Regulation of mean arterial pressure then is kind of a complicated dance of all the various factors that we've been talking about thus far. We need to regulate mean arterial pressure so that we can ensure adequate blood flow to vital organs. Without that pressure, we don't have a driving force. So we maintain homeostasis when it comes to blood pressure, mean arterial pressure. I want you to look first at the box on the left. I like to think, again, my mental image when it comes to regulating the mean arterial pressure is that I have a toolbox. Let me zoom in on here. If you think about, let's say you're building something and you want to put a nail into a board, you're not going to pull out the saw to hammer that nail in. You're going to use the hammer. And so my point in making that is that we're going to have a list of possible things that we could adjust in order to adjust mean arterial pressure. And we're going to manipulate those to either increase or decrease my mean arterial pressure to maintain homeostasis. But we don't necessarily need to use every tool in the toolbox, and we don't always use the same tool. We can use different tools at different times depending on the needs of our body. So let's look at our tools. They can be broken down into two main categories. Category one is to increase cardiac output. And that's probably the go-to method. If we're manipulating mean arterial pressure, most likely we're going to be manipulating cardiac output in a way. The second process is also used, but it tends to be used a little differently. So if we look at cardiac output, on a very basic level, we need to remember that cardiac output is equal to stroke volume times heart rate. Stroke volume, again, is equal to end diastolic volume minus end systolic volume. Stroke rate is affected by blood volume, venous return, contractility, afterload, and so these all participate in either increasing or decreasing the stroke volume. So if I were to separate these into, we'll use yellow for things that increase stroke volume. If blood volume goes up, stroke volume goes up. If blood volume goes up, venous return goes up. If the venous return goes up, the ventricle stretches out. We get longer sarcomere lengths. I don't have that specifically listed, but our end diastolic volume is bigger. And if our end diastolic volume is bigger, then our preload is bigger. That's not listed on here either, but we might as well jot that down because there's that relationship between end diastolic volume and preload that's really quite important. And so as my preload goes up, as my end diastolic volume goes up, as my blood volume goes up, as my ventricle stretches out, as my sarcomere lengths become longer, all of those factors work together to increase contractility. Contractility lowers end systolic volume. By squeezing out more volume of the blood, it increases the ejection fraction. On the other hand, afterload tends to lower stroke volume because it creates this resistance that the stroke volume has to work against. Interestingly enough, while blood volume increases in blood volume, increase venous return and end diastolic volume, they also affect afterload. So blood volume has both a positive and a negative component to it in terms of affecting the volume, so the function of the heart. So if we increase blood volume, most of the time it's going to lead to an increase in cardiac output, but it's also important to understand that it's going to increase afterload. Then we have our systemic vascular resistance, and just as a reminder, this is going to be regulated on a local level, and it's going to be regulated systemically by the sympathetic nervous system primarily. Now, as systemic vascular resistance goes up, our afterload also goes up, and so the higher the systemic vascular resistance, the more the heart has to work to move blood through the circulatory system. And then don't forget, for systemic vascular resistance, we actually have to change the diameter of the blood vessels cause vasoconstriction in many large areas of the body and a significant number of arterioles. If we're just changing a few of them, we're not going to get changes in that systemic vascular resistance. Now let's go over here to this other figure over here. What we're going to do is we're going to look at some equations that I've already taught you. So the first equation that we look at here is one you should be comfortable with, is rate of flow, or flow rate, Q, is equal to delta P divided by R. And you'll recall again that R is equal to 1 over the radius to the 4th power. Consequently, if we do some substitutions, just to kind of put things in perspective, we can substitute cardiac output for the value of Q. So that works. Cardiac output can be used as a value for Q. We can substitute that, and I've been doing that throughout this entire lecture. You'll recall I repeatedly referred to Q total as being equal to cardiac output. Now, mean arterial pressure, we actually can substitute the mean arterial pressure for that delta P. This isn't an exact substitution, but it's pretty darn close. If we're looking at average pressure in the aorta compared to the average pressure in the vena cava, there's quite a big difference there in terms of pressure. And so that mean arterial pressure is a very good estimate for how pressure changes through the circulatory system. And then in terms of systemic vascular resistance, we could easily substitute that for the letter R, the resistance. So total resistance is basically systemic vascular resistance. Why does this matter? Well, this is going to give us an equation. If we rearrange things, first it's going to give us this equation here, where we can see here that the cardiac output is equal to the mean arterial pressure divided by the systemic vascular resistance. And then if we rearrange that equation, we get the equation circled below, where we have cardiac output times systemic vascular resistance. And that's just through simple algebra and rearranging that equation. So this is my toolbox. Let's look at it in more detail. Now here is a much prettier graph. Let me just kind of show you for comparison. Here's my simplified version, and here's a much more elegant and beautiful version that was created, where we can see the different arteries and arterioles and mean arterial pressure and so forth. And so let's highlight some of these factors. If we look at, for example, afterload, that's basically resistance. That's a huge amount of resistance due to the blood volume in the aorta. And afterload is increased. What we end up doing is my systemic vascular resistance goes up. It's kind of like causing a traffic jam on the freeway. So we're going to use another analogy. Let's imagine that the aorta in this case is my freeway. Okay, and now each of these arteries is going to be an exit, okay, on the freeway. So if we were to look at, I take the 10 freeway to Mount Sac, and there's a number of exits I could take. I could take Citrus, for example, to get to Mount Sac. I can take Grand. If I really wanted to, I could go past Grand and take, I think it's called Hoyt. If I wanted to, I could also, in theory, take Azusa. And so these are my exits. And so imagine that everybody's trying to get to Mount Sac. Everybody in the Los Angeles County is trying to get to Mount Sac. And most of these people are taking the 10 freeway. We're going to have a tremendous amount of traffic on this 10 freeway, right? But we have a number of routes. So if traffic slows down, I might choose Azusa. Maybe I'm going to choose Citrus. Maybe I'm going to choose a different route. But now let's imagine we have construction. And we're going to create construction on these exit ramps. And so what I'm essentially going to do is narrow those ramps, so you have to move really, really slow. And so everybody has to slow down. Or worse still, maybe I'm going to kind of I'm going to close Azusa. And let's, for good measure, close Citrus. And heck, why don't we go ahead and close Grand too? So now we only have one exit. And what that means is that every car to get to Grand is basically going to take that exit. And you can imagine the pileup. If I can't get my cars off the freeway, they stay there. We ended up with a huge traffic jam with these cars backed up on the freeway. Same thing here. If I cause, now I'm not going to vasoconstrict the arteries, but if I start vasoconstricting my arterioles, then that's going to prevent the blood from exiting the freeway, if you will. And so it ends up being stuck, and it has to stay essentially in the arteries. And if those back up, so my arteries are going to create a backup, and by backup I'm referring to like a traffic jam. So I have a traffic jam of blood volume, so I have an increased amount of blood volume in my arteries, and that's going to give me an increased amount of aortic blood volume, and that's going to increase my afterload. So systemic vascular resistance resists the flow of blood into the arterioles. And this would have to be, again, a large-scale vasoconstriction of a variety of different arterioles if I'm going to get that increase in systemic vascular resistance. And as a consequence, also, systemic vascular resistance is going to reduce my blood flow. So it just makes it harder for me to move blood through the arterioles. I can counteract that by increasing my blood pressure and my cardiac output. So we're going to see a lot of number changes. Then we get our systemic capillaries, which are the site of exchange. They're less important for regulating blood flow. Same thing with the venules, not that important for regulating blood flow, but the venous return is super important for regulating blood flow, and specifically the mean arterial pressure, which blood flow is dependent on that. And in this example, you know, if you remember that the veins and the venules are highly compliant vessels. As I fill, if I pack these veins with blood, some of it's going to pool in usually my lower extremities, my legs, also in my hands, some cases in other areas of the body. But that's going to generate, that's essentially going to move. I'm going to use I'm going to use an analogy. It's not actually accurate, but it gives you a visual picture. So what we're basically doing is the veins expand, and lacking those elastic fibers, we're essentially going to store blood. And so sometimes my visual image is, think of this as a storage unit. You know, I'm going to go and buy a storage unit, and I'm going to store all my Christmas stuff in there or whatever. And then when I need it, I'm going to take it back out. And so, you know, we are in essence changing my venous return through whether or not my veins are storing blood. And how do we take it back out? Well, that's going to be manipulating skeletal muscle activity, respiratory system activity, blood volume, and so forth. And so these are going to affect the blood volume returning to the heart, which is essentially venous return. And all of these then, of course, play together to regulate my cardiac output. And together, everything here determines my mean arterial pressure, and that's critical because that's my driving force for blood through the circulatory system.